We begin a very long time ago, further back than human memory can reach, further back than the oldest stone tools, further back than the first forests. We begin 66 million years ago, in a world so different from our own that it would be almost unrecognizable. And yet it is the same Earth, the same rock beneath everything, the same oceans filling the same general basins, the same sun in the sky above. The world at this time is warm, warmer than the world we know today. There are no polar ice caps. The poles are cold, but not frozen over. Sea levels are higher than today. Shallow inland seas cover parts of what are now continents. In North America, a shallow body of water called the Western Interior Seaway runs from north to south. It divides the continent into two large landmasses, east and west, separated by this warm, shallow sea. The continents themselves are arranged differently. They are in the positions that hundreds of millions of years of slow movement have brought them to, moving at the pace of growing fingernails, a few centimeters each year. Over millions of years, this slow drift reshapes the world entirely. At the time we are speaking of, the continents look broadly similar to today, but not exactly. India has not yet fully collided with Asia. Australia is further south. The Atlantic Ocean is narrower. The climate is consistent across most of the world. Warm and wet, forests grow widely. Flowering plants, which evolved not long before this period in geological terms, are now spreading across the landscape. Ferns still cover the ground in many places. Conifers, trees related to modern pines and sequoias, form forests across much of the world. And in this warm, forested world, the dinosaurs live. They have been here for a very long time. Dinosaurs first appear in the fossil record roughly 230 million years ago. They have been the dominant large land animals for over 160 million years. This is a period of time so vast it is difficult to comprehend. Compared to the time the dinosaurs dominated the Earth, the entire history of modern humans is a small fraction. By 66 million years ago, the dinosaurs have diversified into an enormous range of forms. They fill almost every ecological role that large land animals can fill. Some eat plants. Some eat other animals. Some are enormous. Some are small. Some walk on 4 legs. Some walk on 2. Some have elaborate crests and frills and horns. The largest plant-eating dinosaurs of this period belong to a group called the hadrosaurs. These are the duck-billed dinosaurs. They live in large herds. They move across the landscape in groups. They eat the vegetation they find: leaves, ferns, flowering plants. Their teeth are arranged in tightly packed rows. Hundreds of teeth, grinding plant material continuously. When front teeth wear down, new ones grow to replace them. A constantly renewed grinding surface. The ceratopsians are another group of plant eaters. These are the horned dinosaurs. Triceratops is the most familiar to modern eyes. It is a large animal, perhaps 8 or 9 meters in length. 3 horns on its face. A wide bony frill extending from the back of its skull. It grazes on low vegetation. It lives in the western part of what is now North America. The tyrannosaurs are the large predators of this world in the northern hemisphere. Tyrannosaurus rex is the most well-known. It is a large animal, perhaps 12 to 13 meters long, heavy, powerful jaws with large, thick teeth designed not for slicing but for crushing. Can bite through bone. It moves on 2 legs. Its arms are small. The senses are sharp. The sense of smell, in particular, is well developed. Scientists have studied the brain structure of tyrannosaurs and found that the olfactory regions are large. They could likely detect scent from considerable distances. In the southern hemisphere, different predators fill similar roles. The abelisaurids are large predators in what is now South America, Africa, and India. They have similarly small arms, similarly powerful hind legs. A parallel solution evolved independently to the problem of being a large land predator. Smaller predators exist as well. The dromaeosaurids, the raptors, are among the most active hunters. They are smaller than the tyrannosaurs. Some are roughly the size of a turkey. They are feathered. Most of the dinosaurs at this time are believed to have had feathers, or at least some feather-like covering. This is understood from fossils that preserve impressions of feathers in fine-grained rock, and from the fact that birds are the living descendants of a group of small theropod dinosaurs. Birds are, in the most precise scientific sense, a group of dinosaurs that survived. The birds alive today are the direct descendants of small feathered theropod dinosaurs. This is not a matter of debate in modern paleontology. The evidence is clear and detailed. The skeleton of a bird and the skeleton of a small theropod dinosaur share a very large number of features. Hollow bones, a wishbone, the structure of the ankle, the arrangement of the toes. In many ways, a bird is simply a feathered dinosaur that can fly. In the skies above the Cretaceous world, other creatures fly as well. The pterosaurs. These are not dinosaurs. They are a related group of reptiles that took to the air much earlier. They have been flying for over 150 million years by this point. Some of the pterosaurs of the late Cretaceous are enormous. Quetzalcoatlus, found in what is now Texas, has a wingspan estimated at 10 to 11 meters, possibly larger. It is the largest known flying animal in Earth's history. In the oceans, the dominant large predators are not dinosaurs. They are other reptile groups. The mosasaurs are large marine lizards. They are related to modern monitor lizards. Some are enormous. Long, streamlined bodies, powerful tails, conical teeth. They are the top predators of the late Cretaceous seas. The plesiosaurs are also present in the oceans. Long-necked forms with 4 broad paddles and relatively small heads. Shorter-necked forms with large heads and long jaws. They are air-breathing reptiles, surfacing regularly. They have been in the oceans for a very long time. The shallow inland seas teem with life. Fish of many kinds. Ancient sharks, sea turtles, ammonites, coiled, shelled creatures related to the modern nautilus. They range in size from very small to very large. Some ammonites of this period have shells more than a meter across. Their shells are beautiful in their mathematical regularity, coiled in a precise logarithmic spiral. This is the world, full of life, varied and complex, a world that has been building its complexity for hundreds of millions of years. And then something happens, something that arrives from outside the world entirely, from space. A large object is traveling through the solar system. It has been traveling for a very long time, following an orbit around the sun. An orbit that, by a matter of orbital mechanics accumulated over millions of years, brings it onto a path toward the Earth. This object is an asteroid, a rocky body. Its diameter is estimated, from the evidence left behind, at roughly 10 to 15 kilometers. Perhaps a little more. A mountain-sized rock moving through space. It enters the Earth's atmosphere at high speed. The speed of objects crossing the inner solar system is very high. Perhaps 70,000 kilometers per hour, or more. At this speed, the passage through the atmosphere is very brief. The air cannot get out of the way fast enough. Compresses ahead of the asteroid. The compression heats it enormously. The asteroid itself is heated. The surface ablates. Material burns off. It strikes the Earth in what is now the Yucatan Peninsula of Mexico. The impact site is called Chicxulub. The name comes from the nearest modern town. The crater it creates is enormous, roughly 180 kilometers across, and perhaps 20 kilometers deep at the point of impact. The energy released by this impact is almost impossible to describe in familiar terms. Scientists express it in terms of nuclear weapons. The energy is estimated to be equivalent to billions of nuclear weapons detonating simultaneously. But even this comparison is difficult to hold in the mind. It is simply an enormous amount of energy, released in an instant, into the surface of the Earth. At the impact site, everything within a large radius is destroyed immediately. The rock of the crust is vaporized, melted, thrown outward. A wave of superheated material expands from the impact point. Rocks that were solid become liquid. Liquid becomes vapor. The explosion sends material flying outward and upward, into the atmosphere, into space. The impact sends a shock wave through the Earth itself, through the rock of the crust and mantle. This shock wave triggers earthquakes across the planet. The ground moves in ways it has never moved in the time that these animals have lived on it. The impact happens near the coast. The sea is close. The displacement of the sea generates enormous waves. These waves travel outward from the impact site. They reach coastlines around the Gulf of Mexico and beyond. The scale of these waves is very large. The evidence for them is found in the geological record. Layers of jumbled sediment along ancient coastlines. Material that was moved by water. Moved all at once very quickly. Material thrown into the atmosphere by the impact begins to fall back to Earth. Some of it has been thrown so high into space that it follows a ballistic arc around the planet. It re-enters the atmosphere at high speed. This re-entering material heats the upper atmosphere. Infrared radiation pulses downward. The surface of the Earth, for a period of hours, receives an intense pulse of heat from above. This pulse of radiant heat is believed to have ignited wildfires. Across large areas of the world, dry vegetation catches fire. The fires burn. Smoke rises into the atmosphere. Carbon from the burning vegetation adds to what the impact has already thrown into the sky. The debris and soot and sulfur in the atmosphere begin to block sunlight. The sky darkens, not gradually over years as with a volcanic eruption, but quickly. Within days or weeks, the amount of sunlight reaching the surface of the Earth is drastically reduced. The Earth cools. Without sunlight, photosynthesis cannot proceed normally. Plants cannot make energy from sunlight if sunlight does not reach them. This is the critical moment. This is where the chain of consequences becomes global and permanent. For many forms of life, photosynthesis is the foundation of almost all life on Earth. Plants, algae, and certain bacteria capture energy from sunlight. They use it to build sugars from carbon dioxide and water. These sugars are the energy currency that flows through every ecosystem. Animals eat plants. Other animals eat those animals. Fungi and bacteria break down dead material. All of it ultimately running on the energy captured from sunlight by photosynthesis. When photosynthesis fails, the foundation collapses. Plants die. The animals that eat plants run out of food. The animals that eat those animals also run out of food. The collapse propagates upward through the food chain. The immediate aftermath of the impact is a period of darkness and cold, sometimes called impact winter, similar in some ways to the volcanic winter that a large eruption can produce, but more severe and more sudden. In the oceans, phytoplankton are the foundation of the food web. These are microscopic photosynthetic organisms. They float near the surface of the ocean where sunlight penetrates. When sunlight is blocked, they die, and the entire ocean food web above them is disrupted. The ammonites disappear entirely in this event. After surviving for hundreds of millions of years, through many previous crises, they do not survive this one. Their coiled shells stop appearing in the fossil record above a certain layer. A line in the rock. Below the line, ammonites. Above the line, none. The mosasaurs disappear. The plesiosaurs disappear. The pterosaurs disappear. The non-avian dinosaurs disappear. All of them. Every large species. Every species of hadrosaur. Every ceratopsian. Every tyrannosaur. Every sauropod. Every ankylosaur. Every pachycephalosaur, gone. Above a certain layer in the rock, they are simply not there anymore. This layer in the rock is found all over the world. In the chalk cliffs of Denmark, in the badlands of Montana, in the limestone of Spain, in the rock of New Zealand, in ancient seabed sediments from the deep ocean. Everywhere scientists look for it, the layer is there. A thin layer, sometimes just a centimeter or two thick. Rich in iridium. Iridium is a metal that is rare in the Earth's crust. It is more common in asteroids. When this thin layer in the rock is analyzed chemically, it contains far more iridium than the rock above or below it. This iridium comes from the asteroid, from the vaporized material of the impactor, dispersed around the world as it fell back to Earth. This layer is called the Cretaceous-Paleogene boundary, or sometimes the KPG boundary. The K comes from the German word for Cretaceous, Kreide. The PG stands for Paleogene, the period that follows. Below this line, the Cretaceous world. Above it, a different world. The line between them is marked by iridium and extinction. The discovery of the iridium layer in 1980 was a significant moment in the scientific understanding of this event. The physicist Luis Alvarez and his son, the geologist Walter Alvarez, along with colleagues, published a paper proposing that the iridium layer was evidence of a large asteroid impact, and that this impact was the cause of the mass extinction. At the time, this was a controversial idea. Many scientists were skeptical. Over the following decades, the evidence accumulated. The Chicxulub crater was identified. It had been found earlier in the 1970s by scientists working for a Mexican oil company, but its connection to the extinction event was not recognized immediately. Later analysis confirmed that the crater dated to exactly the right time. 66 million years ago, the same age as the iridium layer, the same age as the extinction. The Chicxulub crater is now buried under kilometers of rock and sediment, and partly under the waters of the Gulf of Mexico. Cannot be seen on the surface, but it can be detected. Gravity measurements show the circular structure. Drill cores through the rock reveal the melted and shattered material of the impact. The crater is real. It is there. Beneath the Yucatan Peninsula, a ring of cenotes, natural water-filled sinkholes, follows the edge of the buried crater. These sinkholes are where the fractured rock of the crater rim allows water to move more easily through the limestone. Local people have used them for thousands of years. Water sources in a region without rivers. The evidence now strongly supports the asteroid impact as the primary cause of the end Cretaceous extinction. There is another factor that scientists also discuss: a period of very large volcanic eruptions in what is now India. These eruptions, called the Deccan Traps, produced enormous amounts of lava. They also released gases into the atmosphere, including carbon dioxide and sulfur dioxide. The Deccan eruptions were happening before the asteroid impact and continued afterward. They may have already been stressing some ecosystems. The relationship between the Deccan eruptions and the extinction is studied carefully. But most scientists conclude that the asteroid impact is the primary driver. Not everything dies. This is important to understand. The extinction at the end of the Cretaceous is a mass extinction. A large proportion of species disappear, but not all life ends. Far from it. Some groups survive, and understanding what survived and why helps us understand the nature of the extinction. Small animals survive better than large ones. In the immediate aftermath of the impact, food is scarce. A small animal needs much less food than a large one. A small mammal, sheltering underground, eating seeds or insects or whatever it can find, can persist through conditions that would kill a large animal quickly. The mammals of the late Cretaceous are mostly small. They have been living in the shadow of the dinosaurs for over 100 million years. Small, nocturnal, burrowing creatures. Some are the size of a shrew. Some are a little larger. None are very large. And this smallness is, in the terrible conditions following the impact, an advantage. Some species of turtle survive. Crocodilians survive. These are slow-metabolizing animals. They can go for very long periods without eating. They can survive on very little. Some fish survive. Some amphibians survive. Many insects survive. Many plants survive, though severely reduced. The seeds and roots of plants can persist underground through conditions that kill the above-ground parts. When conditions improve, they can regrow, and the birds survive, or at least some lineages of birds survive. Not all of them. Some bird lineages are also lost in the extinction. But the lineage that gives rise to all modern birds makes it through. Small, perhaps ground-dwelling, capable of eating seeds. They survive. The world after the impact is a quieter world. A world with much less large life. The forests are damaged. Many trees are dead. Ferns, which can regrow quickly from underground parts, are among the first plants to spread across the damaged landscape. The fossil record shows a fern spike in the period immediately after the impact. A sudden abundance of fern spores in the sediment layers just above the KPG boundary. A world of ferns, recovering. The surviving animals move through this damaged landscape. They eat what they can find. They shelter where they can. Slowly, over thousands of years, the atmosphere clears. Sunlight returns. The impact winter ends. The earth begins to warm again. And in this changed world, the survivors begin to diversify. The ecological roles that the non-avian dinosaurs occupied are now empty. The large plant-eater role, the large predator role, the medium-sized browser, the canopy dweller. These niches are vacant, and over millions of years, the surviving groups evolve to fill them. The mammals are the group that most dramatically diversifies after the extinction. Free from the competitive presence of the large dinosaurs, and with a world of open ecological opportunity around them, the mammals evolve rapidly. In geological terms, rapidly, over millions of years. They grow larger, they diversify, they spread into every habitat on land. They also return to the oceans. The ancestors of whales and dolphins are land mammals that move back into the water over millions of years. By about 50 million years ago, the world already looks much more familiar. Forests with recognizable trees, mammals of many kinds, early horses, early whales in the oceans, birds diversifying into many forms. The world 66 million years ago was not our world, but it became our world through the slow accumulation of evolutionary change, through extinction and diversification and adaptation. The world we live in is the world that was left after the asteroid, shaped by what survived, shaped by the opportunities the survivors found in the emptied landscape. The dinosaurs are not entirely gone. This is worth saying clearly. The birds are dinosaurs. Every sparrow at a feeder, every crow on a wire, every albatross crossing the open ocean, every penguin standing on Antarctic ice. These are dinosaurs, living dinosaurs, the descendants of the small feathered theropods that survived the impact winter. There are roughly 10,000 species of birds alive today, more species than all the mammals put together. The dinosaurs did not disappear. One lineage of them found its way through the worst of it, and that lineage gave rise to the most diverse group of large land vertebrates on Earth today. The evidence for what happened 66 million years ago is now extensive. The iridium layer, the Chicxulub crater, the shocked quartz found around the world at the KPG boundary, quartz crystals that show distinctive patterns of fracture produced only by very high-pressure impacts, the glass spherules, tiny beads of melted rock that solidified as they fell through the atmosphere. All of this evidence from many different kinds of rock, from many different places in the world, tells the same story. A large object struck the Earth, and the world changed. The KPG extinction is one of 5 major mass extinctions identified in the fossil record. It is not the largest. The largest occurred about 252 million years ago, the end-Permian extinction. It is sometimes called the Great Dying. It killed perhaps 90% of all marine species, and perhaps 70% of land vertebrate species. Its causes are different. Enormous volcanic eruptions in what is now Siberia, rapid climate change, ocean acidification. The end Permian is in some ways more severe, but the end Cretaceous is the most recent, and it is the one that ended the reign of the non-avian dinosaurs, and opened the door to the age of mammals, and eventually, very much eventually, to us. We are here in part because of what happened 66 million years ago. The small mammals that survived the impact winter, the ones that burrowed underground and ate seeds and insects through the darkness. They are our ancestors, many, many generations removed, uncountable generations, but ours nonetheless. We carry in our biology traces of that long history. The basic structure of the mammalian skeleton, the warm blood, the hair, the complex brain. These things were all present in simpler form in the small creatures that survived the impact winter, and they have been building and developing and diversifying ever since. 66 million years is a very long time. The asteroid that struck the Earth in that moment is gone, destroyed in the impact, scattered around the world as iridium and glass beads and dust. The crater it left is buried and invisible from the surface. The animals it killed are known only from their bones, preserved in rock. The world it created, this world, is the one we live in. We slow down now. The narration comes gently toward its end. 66 million years ago, on a warm afternoon in what is now Montana, a triceratops moves slowly through a fern meadow. It lowers its head. It eats. The sky above is blue and clear. The sun is warm. The world is full. And then, somewhere above, a light appears. brighter than the sun, growing quickly, and the world changes. And out of that change, eventually, everything that came after. The fern forests of the recovery, the diversifying mammals, the ancient horses and early whales, the spreading grasslands of a later age, the first hominids in Africa, and then, much later, a small group of people sitting around a fire, looking up at the same stars that shone over the dinosaurs, wondering where they came from. The story of the extinction is also the story of the beginning, of what came after, of the world that was built from the wreckage of the old one. A slow, patient, millions of years long rebuilding that eventually produced every living thing on Earth today. The night is quiet. The stars are out. Somewhere underground, the iridium layer lies exactly where it has always been. A thin line of memory in the rock, 66 million years old, marking a boundary between two worlds. And above that line, the world that followed. Our world, still here, still turning, still full of life.